Okay. Hi everyone. For those of you that don't know who I am, I'm part of the JIT compilation control team. Um, in this talk, I'm going to share an interesting work that I was involved in for the past few months. I will start off the presentation with some background information on related technologies, and I will follow that by explaining what problems we've encountered and how it resulted in this solution we call Portable AOT. Then in the last part, I will cover the details of the solution as well as what has been completed and future work. So I'm going to start with introducing you to just-in-time compilation and ahead-of-time compilation. Just in case anyone isn't familiar with them. A JIT compilation takes place during the execution of programs. Some people also call this dynamic compilation. This way of compilation allows the compiler to know how the running program executes and what hardware the program runs on. As a result, it knows exactly what optimizations can be applied to the running program and what hardware features can be exploited. An example of a compiler that uses JIT compilation is the JIT compiler that's inside the Java virtual machine. Another type of compilation, ahead of time compilation, takes place before the execution of programs. It is also known as static compilation. A C++ compiler would be a good example. Unlike a JIT compilation, AOT does not have access to the program's actual runtime environment. This means it has to be less aggressive in terms of optimizations, or else you run into the risk of the code being incompatible in certain runtime environments. To give you one example, if the compiler does AOT optimization too aggressively, meaning the compiler try to exploit all the newest processor features, then there's a high chance your program won't run on older generation processors. And due to the fact that the compiler is more conservative with optimizations, AOT compile code will be slower than JIT compile code, which brings us to the graph on the right here. This graph shows the advantages of the two types of compilations. JIT gives you higher steady state throughput because it is capable of doing more optimizations. While AOT gives you lower footprint as you don't need a JIT compiler at runtime that takes up resources during the execution of the program. And AOT also gives you faster startup and ramp up because the AOT compile code are already available at startup, unlike the JIT compile code. Now I'm going to bring OpenJ9 into the picture. So which type of compilation does OpenJ9 use? OpenJ9 uses both types of compilation. It can run AOT compile codes at startup for the purpose of achieving faster startup and ramp up as well as lower memory footprint. Then over time, it will recompile the AOT compilations into JIT compilations to achieve higher steady state throughput. What OpenJ9 is doing is trying to get the best from both worlds. However, it's worth noting that the way OpenJ9 uses AOT is different from a conventional static compiler. A conventional static compiler like a C++ compiler generates AOT at compile time and produces an executable binary for people to run. OpenJ9 generates AOT code at runtime, just like how it generates JIT compile code. It does not generate standalone executable or binaries. So for OpenJ9 to actually use the AOT compile codes, it needs to store them somewhere ahead of time. This is where OpenJ9's shared class cache feature comes into play. The shared class cache, or SCC, is a persistent cache for storing AOT compile code generated by OpenJ9's compiler. Note that AOT compile code is not the only thing that the SCC stores, but since the other things are out of scope for this presentation, I'm not going to cover them. Okay, so how does OpenJ9 use this cache? When the OpenJ9 JVM runs for the first time, it is going to generate AOT compile code and store them into the shared class cache. Then subsequent runs can pick up the AOT code from the shared class cache and benefit from it. We call this first run with an empty cache, the code run, and the subsequent runs, the worm run. If you see the figure on the right, we have 3 instances of the JVM on one node. Let's say JVM 0 started the earliest, so it will be the code run. It starts up and the AOT compiler fills up the SCC with AOT compile code. Then JVM instances 1 and 2 can pick up the AOT compile code from the SCC to get faster startup and ramp up performance. And what I just described is the workflow of OpenJ9's AOT SCC technology. I'll be using this term AOT SCC a lot throughout the presentation. I think we have finished the background information on related technologies. Now let's get into the problem and the solution. With the emergence of containers and the microservices architecture, where we have lots and lots of lightweight applications that are constantly being scaled up and down, startup performance becomes very important in the cloud, which in turn makes this AOT SCC technology extremely important to OpenJ9 in the cloud. However, there are some usability issues with this technology in the cloud. In the cloud, we normally put applications inside Docker containers, and if we just naively use the AOT SCC technology inside containers, we will always be doing code runs. The reason for that is the AOT generated by the first run cannot be persisted since we're in containers. Data generated inside Docker containers get thrown away after it shuts down. So in conclusion, to be able to use the AOT code in containers, we need to find a way to persist the SCC in the cloud. The first solution that comes to mind is to persist SCC using a shared volume. You will need a share volume on each node for the containers on that node to share AOT code. Again, if you look at the figure on the right, how this solution works is in a cloud environment, container orchestrator pulls the image and launches the containers on the 2 node we have here. Each node has its own volume that persists the AOT. And the problem with this solution is that it does not work very well when we have multiple machines. If the containers land on different nodes, you have to start fresh again. It seems okay when we have 2 nodes here, but if you have hundreds of nodes, then that's hundreds of code runs, and that's the main issue with this solution. Additionally, users have to create the shared volume themselves and manually map them to the containers, which is not ideal either. So the team came up with a better solution. Instead of creating shared volumes, we can embed the shared class cache into the Docker container, like is shown in this figure on the right. How this works is that when you build the image, it's going to invoke the JVM to give the application a run that will populate the AOT in the shared class cache. So once the image is built, we have a warm cache in the image. This way, we basically eliminated code runs altogether. So now, as soon as the container is instantiated, it will have a copy of the SCC that it can benefit from immediately. And it doesn't matter which machine the container lands on, we always have access to a warm cache. Another important benefit is that there is no extra work required from the user to enable the AOT SCC feature. They don't need to worry about mapping volumes to their containers to be able to use this feature. And for those of you who worked with Docker images before, you may wonder what happens when the image we build has multiple layers, and that's quite a common use case. For example, you can have an OpenJ9 image layer, and on top of that, you have an OpenLiberty layer, and then on top of that, you have the actual application business logic layer, and these three layers may have their own shared class caches, and that may complicate things. For this issue, the team introduced a multi-layer shared class cache feature, which allows the upper layer to seamlessly extend the lower layer SCC. So in the end, it can make it look like we just have a single shared class cache in a multi-layered image. Not going to get into its implementation details. It's not the focus of today's presentation. And we already had a presentation on it. I just wanted to put it out there that we're expecting multi-layer Docker images, and we already solved that issue. So this seems to be a much better solution than the previous one, and it is the solution that the team is delivering. The issue for this solution is that we now need to consider and address any portability issues with our AOT code, because unlike how AOT SCC is normally used, where AOT code stays on the same machine, AOT code in this solution moves around with the container. The build environment is not going to be the same as the runtime environment anymore. Also, in the multi-layered image case, each layer's SCC is likely generated with a different JVM instance with different configurations. If these different configurations cannot share AOT code with each other, then we have a problem. And after investigation, we did find a few portability issues with OpenJ9's AOT. So let's take a look at the portability issues in detail. First off, due to the way the OpenJ9 compiler exploits CPU features, its AOT is not portable across CPUs of different microarchitectures. So when OpenJ9 generates AOT code, it exploits the host CPU's feature set for optimizations, just like what it does with JIT compilations. This is a portability issue because if the build time CPU is of newer generation, the code won't be portable to older generation CPUs. And secondly, due to the implementation of OpenJ9's compressed references, its AOT is not portable across JVMs of different heap sizes. I'll briefly explain why that's the case. compressed reference is a technique that OpenJ9 uses to improve the memory efficiency and performance of 64-bit applications by shifting and trimming the heap object references down to 32-bit. Compressed reference affects the way AOT code is generated. Depending on the amount of shift that the compressed reference use, AOT code will be generated differently. The amount of shift is determined by the heap size. So the reason AOT code is not portable across different heap sizes is because it's not portable across different shift values. Another minor portability issue is that due to the optimizations we do for constant size heap, OpenJ9's AOT is not portable across constant size heap and variable size heap. The one thing we found is that when the compiler realizes the heap is fixed in size, it will generate a simpler write barrier sequence, which will not work for a variable size heap. And lastly, another portability issue is related to GC policies. AOT code is not portable across JVMs with different GC policies. With these portability issues in mind, I'm going to talk about how we address each issue to improve AOT portability. And I think by now I have provided you with all the context you need to understand the definition of portable AOT. So I'm going to define it. Portable AOT is AOT code with improved portability that makes it runnable in different environments, and it will be controlled by an option. I'll talk about how the option works after we have gone through the portability improvement implementation. Okay. Starting with addressing the portability issue caused by CPU feature exploitation. The solution is to try to reduce down the number of CPU features that we exploit. We are only going to utilize the most common ones, so that the majority of the CPUs can understand and run the code. In the implementation, instead of using the underlying CPU feature set for AOT compilations, we use a relatively old processor feature set that we call the portable CPU feature set. This will improve portability drastically. It's similar to how a static compiler like GCC ensures the portability of its generated binaries. The figure I have here on the right is a simplified version of the implementation. The JVM is going to issue a compilation request at the top. If it's a JIT compilation, then it will use the underlying CPU's feature set for optimizations and code generations. If it's a AOT compilation, then it's going to check whether we want portable AOT or not. If we don't want portable AOT, we're still going to use the underlying CPU's feature set. Otherwise, we'll use the portable CPU feature set. In the end, we store the code in the shared class cache. We made this decision because we recognize that CPU feature exploitations are not very important for OpenJ9's AOT code. AOT's whole purpose in OpenJ9 is to be faster than the JVM interpreter. It's only there to help the application start up and ramp up faster. The steady state throughput is not affected by us going back to an older CPU feature set, simply because by the time we reach steady state, the AOT code is already replaced by JIT code. And I have an experiment to back up this claim. So our experiment involves running the DayTrader 7 benchmark on an Intel Skylake CPU, a CPU microarchitecture from 2015. For the portable feature set that will be used by the portable AOT compilations, we picked the Sandy Bridge CPU feature set, which is a relatively old CPU microarchitecture from 2011. The baseline run is to compile both AOT and JIT using the host CPU, which is the Skylake CPU. The target run is to compile AOT using the older CPU set and JIT using the host CPU set. As expected, we did not observe any steady state throughput penalty from the experiment. Moving on to addressing the portability issue caused by the compressed reference implementation. Just to recap, AOT code is not portable across JVMs with different compressed reference shift values. And the shift value is determined by the heap size. Our solution is to make the JVMs that want to share AOT code use the same shift value. That way, AOT becomes portable across different heap sizes. And it really comes down to which shift value to pick. First off, not all shift values can be used on all heap sizes. For example, shift 0 can only be used on JVMs with a heap size under 3 GB, and a shift value of 3 can be used on heap size up to less than 28 GB. Shift 4 can be used on heap size less than 57 GB. So a shift value of 0 performs better than shift value of 3, and shift value of 3 performs better than 4. By default, we always go for the smallest possible shift value we can use so that we get the best performance out of it. The performance penalty of shift 4 over shift 0 is just too much for us, and shift 0 does not improve the portability at all, since the range of heap sizes it covers is too limited, only up to 3 GB. So in the end, we picked shift 3. Fixing OJVM to shift 3 will allow heap sizes up to 28 GB to share AOT code with each other. The downside of the solution is we have performance penalty for JVMs with heap size under 3 GB, because originally heaps under 3 GB can use shift 0, but we're forcing it to use shift 3 now. Yeah, and we didn't resolve the portability issue for heap sizes over 28 GB. We're not worried too much about heap sizes over 28 GB because it is a rather uncommon range for heap sizes in containers. However, we do care more about the performance penalty we suffer for smaller heaps under 3 GB. So we did an extensive amount of experiments on this. In the end, we got 1 to 2% steady state throughput drop on x86 and Z, and a 1.5 to 3.5% drop on power. Yeah, so we're still not sure if the performance penalty on power is going to stay at 3.5%, as previous experiments suggested a lower percentage. So this is still under investigation. We understand that when it comes to portability and performance, it's always going to be a trade-off. So we're accepting this penalty and moving forward with the solution. Also keep in mind that the performance penalty only exists when the user wants to have portable AOT code. As for the other portability issue, which is that the fixed size heap optimizations are not portable to variable size heap JVMs, the solution is to turn off the fixed size heap optimizations for portable AOT. We have not gotten to the development of this yet, so don't have any performance number to show right now. And for the portability issue where different GC policies can't share AOT, we do not think this is a common use case for the user to change their application's GC policy from run to run. Therefore, this one is not in the plan right now. That's pretty much it for the details of the portable AOT solution. And here's the option that we'll be using. The reason we named it portable shared cache instead of portable AOT is because portable AOT is just one part of the mission. The goal is to actually have a portable shared class cache for the cloud, and we are only addressing AOT portability because that's currently the only thing inside shared class cache that's not portable. When OpenJ9 runs inside a container, we turn on the option by default, as we know that it's most likely operating in the cloud and needs portable AOT. It can be turned off if the user doesn't need AOT portability by using minus portable shared cache outside of and outside of containers, it's turned off by default, as we don't want the users to pay the performance penalty if they're not going to run in the cloud. And they have the option to turn it on by using plus portable AOT plus portable shared cache. Okay. Sorry. Yeah. Now to progress update and future work. The portable CPU feature set work, which allows different CPUs to share AOT, is completed on x86, Power, and Z, and it's already available on x86 in the current release. On Power and Z, the work has been completed and will be available in the next release. The work on fixing the compressed reference shift to 3, which allows different heap sizes to have portable AOT, is completed and will be available in the upcoming release. Disable fixed size heap optimizations is expected to be completed by 0.24 release. A future work item to allow users to specify their own portable CPU feature set through a JVM option is expected to be completed later, maybe in 0.25 release. And that concludes my presentation. Thank you for everyone's attention, and let me know if there's anything unclear to you, I guess.
Thanks, Harry. Any questions for Harry?